Additive manufacturing eliminated material waste and made complex geometry essentially free. By building objects layer by layer, it stripped away the traditional constraints of milling and molding, ultimately improvising the production lines across the entire globe. This layer-by-layer versatility scales across widely different industries. Engineers use it to fabricate lightweight, hollow lattice frameworks for aerospace components, and doctors use it to print highly customized titanium prosthetics for individual patients. But standard 3D printers don't offer the same practice as they have a limitation. Once they cool and leave the print bed, they are physically dead. They cannot adapt, move, or react to their environment. Traditional additive manufacturing solves the problem of geometry. It perfects the object's form, but it provides zero built-in function. To solve this, researchers are developing 4D printing, the pursuit of manufactured objects that physically transform, act, and react post-production. Achieving this fourth dimension, time does not require a new type of hardware. Instead, engineers are altering the chemical makeup of the printing material itself. By loading the raw polymer with active ingredients, we can shift from printing a static plastic shell to printing an active, responsive machine. One of the most effective active materials is the magnetic composite filament. We start with standard, flexible polymer matrix and mix in microscopic magnetic particles, usually metals like iron or neodymium. In their raw state, these particles are scattered chaotically inside the plastic. As the material heats and extrudes through the narrow nozzle, the chaos aligns into a rigid directional pattern, embedding a permanent magnetic signature. Because the internal structure is now uniformly aligned, the resulting object will physically twist, bend, or pull when it enters an external magnetic field. Engineers are no longer restricted to printing passive structures. They can print programmable, localized forces that replace the need for traditional mechanical parts. We can see this applied directly to modern electronics. Standard high-frequency energy transforms slack, flat, laminated metal sheets together, which inevitably leaves tiny air gaps that leak electrical energy. By 3D printing a solid, toroidal or donut-shaped magnetic core out of composite filament, engineers eliminate those air gaps entirely. This creates a custom-fit, hyper-efficient component that concentrates the magnetic flux and saves both power and physical space. In internal medicine, the application shifts from power generation to directive delivery. Doctors can print a biocompatible polymer scaffold loaded with magnetic nanoparticles and safely implant it inside a patient. This chart displays the magnetic heating rates and shape recovery performance of these specialized biomedical polymers. When a doctor applies an external alternating magnetic field to the patient, the nanoparticles inside the scaffold vibrate and generate heat, a process called hyperthermia. This precisely melts the surrounding polymer layers to release a specific dose of medication. Magnetic composites allow medical professionals to trigger specific physical and chemical reactions remotely, bypassing both internal mechanical assemblies and invasive secondary surgeries. In the field of soft robotics, engineers face a difficult challenge: designing a machine that moves without relying on heavy batteries, stiff wires, or electric motors. When an unseen magnetic field is introduced into a 3D printed polymer claw, the soft plastic smoothly curls closed to grip an object on its own. The embedded metal particles aggressively attract toward the invisible magnetic field. Because they are permanently locked inside the flexible plastic housing, they drag the polymer with them, forcing the entire structure to bend or crawl. This integrates the shape that are already a reality. By translating invisible magnetic fields into kinetic energy, simple printed plastic acts as remote-controlled autonomous objects. Global manufacturing is now shifting from producing static structural shapes to programming dynamic behaviors directly into raw materials. This Venn diagram shows the clear overlap of major industries like digital electronics and aerospace united by 4D printing. By printing the functionality directly into the object, engineers drastically shorten the supply chain, eliminating the need to source disparate parts. Traditional manufacturing requires bolting together a plastic housing, a metal motor, and an electronic sensor. Now manufacturers can print a single unified smart part that executes all those functions at once. Physical materials are becoming as adaptable, programmable, and adaptable digital software. Standard 3D printing taught us how to quickly build the shapes of the modern world. Magnetic filament gives us the ability to print the machine.